If anyone's ready, can go ahead and start.
Hi, Professor. Can I go first?
Sure.
Thank you. All right. Can you see my screen?
Yes.
All right.
Yes, go ahead.
Okay, perfect. Thanks. So a person has 100 light bulbs whose lifetimes are independent exponentials with mean 5 hours. If the bulbs are used one at a time with a failed bulb being replaced immediately by a new one, approximate the probability that there is still a working bulb after 525 hours. So we still need mu and the variance. So we know that the number of light bulbs is 100. The mean says that it's 5 hours, so it's in time. And to get mu, I just switched it around so that you can make it a multiplication and not just division. So you could do the number of hours times the mean, which gets you 500. And then the variance is 100 times 25, which is 2500. But that's the variance squared. So then you have to find the single variance, which means you take the square root, which is 50. And then it says that after 525 hours, so not at 525 hours, but you need to do that when you're finding the probability. So 1 minus the probability of x less than or equal to 525. And then I used what we learned on the textbook, which I do not know how to pronounce well, but it was like Chebyshev thing, inequality. So I did that.
Chebyshev.
Chebyshev.
Inequality.
So I used the total amount, which was 525 hours minus the 500, and then over the 50, which we got from doing the variance work above. And then that went down to 0.5. And then on the chart, it was 0.6915, but I knew I had to subtract 1 because it's x more than 525, which got me 0.3085. So that means that there's like a 30% that there's still a working bulb after 525 hours, which is very interesting.
Very nice. Great.
Thank you. Thank you.
Great. Thank you.
I have 8.1.
Okay.
Short. Suppose that x is a random variable with mean and variance both equal to 20. What can be said about the probability of x between 0 and 40? So given that mean, which is mu, which is equal to 20, and variance, which is sigma squared equal to 20, then by Chebyshev's inequality, the probability of x between 0 and 40 is equivalent to the probability of absolute value of x minus 20 greater than or equal to 20, which is equal to 1 minus the probability of absolute value of x minus 20 less than 20, which means that the probability of the absolute value of x minus 20 less than 20 is greater than or equal to 1 minus 20 over 20 squared, which is equal to 19 over 20, which means that the probability of x between 0 and 40 is greater than or equal to 19 over 20. And that's it.
Sorry, I was talking to myself. I muted myself. Yeah, who's next? Who's going next?
I'll go. Hi.
Thank you, Audrey.
I'm doing 8.5. It says 50 numbers are rounded off to the nearest integer and then summed. If the individual round off errors are uniformly distributed over minus 0.5 and 0.5, approximate the probability that the resultant sum differs from the exact sum by more than 3. So the mean, our expected value would be 0.5 plus minus 0.5 divided by 2, which is 0. And the variance is minus 5. Minus 0.5 minus 0.5 squared over 12, which is 1/12. And the standard deviation is the square root of the variance, which is 0.289. It says 50 numbers. So we multiply the standard deviation by the square root of the 50 numbers, and we get 2.0435. And the probability that the resultant sum differs the exact sum by more than 3 is 1 minus probability, 1 minus p, minus 3, standard error at 3, and then convert into standard normal variable, we get minus 3 minus 0 over 2.041, and positive 3 minus 0 over 2.041. Both answers, the first answer is minus 1.4699, and the second answer is positive 1.4699. And the z-scores of these are 0.9292 and 0.0708. We minus the first one from 1, and we get 0.078, and when I add both, we get 0.1416. And that's the probability resultant sum more than 3.
Okay. All right.
Thank you.
Thank you, Anjali. Next one.
Hi, Professor. Good evening.
Hello, good evening, Kara.
I'm going next. Professor, can you see my screen?
Yeah.
Okay, I'm going to present 8.2. From the past experience, a professor knows that the test score of a student taking her final examination is a random variable with mean 75. So we have to find 3 parts which are given below. A part is saying given an upper bound for the probability that a student's test score will exceed 85. B part, we have to find, suppose in addition that the professor knows that the variance of a student's test score is equal to 25. What can be said about the probability that a student will score between 65 and 85? And C part, we have to find how many students would have to take the examination to ensure with the probability at least 0.9 that the class average would be within 5 of 75. Do not use the central limit theorem. So part A, according to the Markov inequality, probability x greater than a less than equal to expected value of x over a. So in the question, it's given that we have the value 85, probability into x greater than 85 less than equal to expected value of x over 85. After putting expected value 75 over 85, so we have upper bound to the probability is equal to 75 over 85, which is equal to 15 over 17. So for the B part, from the given information, the variance is 25. This implies 1 over 4. Use Chebyshev's inequality to find probability into 65 less than x less than 85. So probability into x minus 75, we have to take on a mod greater than equal to 10, which is equal to less than equal to a variance scale. Sorry, variance over 10 to the raised to power 10 scale. So probability into x minus 75 greater than 10, which is equal to, we have said that it's equal to 1 over 4, and after taking the complement, it will be equal to 3 over 4. Like we have to find probability into 65 less than x less than 85, so for that it will be greater than equal to 3 over 5. So for the part C, use Chebyshev's inequality property because we cannot use the central limit theorem here. So probability into x1 plus x2 tn xn over n minus mu less than sigma less than equal to is 1 minus sigma square over n epsilon square. So after putting the value in it, we have 1 minus sigma square over n 5 square, which will equal to 25n greater than equal to 0.9. And here it will be sigma square over 25 less than 25n less than equal to 0.1. And then after putting the value of n, we will get that sigma square over 25 into 0.1. So we from this solving this, we will get that n greater than equal to 1 over 0.1. So n greater than equal to 10. Therefore, the at least 10 students would be have to take the exam.
Nice.
Thank you, Professor.
Nice. Thank you, Kara. Okay, we have Darius, Catherine.
Okay, all right. So this is just from 6.55. So we're just looking to get the what is that, the density function for a distribution of the range. So we have two samples, x1 and x2. They're uniformly distributed over 0 to 1, so they're going to have just what is that, the f of x equals 2x for both. So I just calculate the joint continuous density function. And then once we have that, we just differentiate to get the distribution density function of the range, which is below.
Hold on. I'm trying. Okay. You define R equals that. I see. Okay.
Yeah, the range, right? Yeah.
Okay. Yeah. Okay, nice.
Can you see my page?
Kami, yes.
Sorry, I'm a bit nervous.
Oh, don't be. Yeah, just try.
Okay, so I did 8.6, A die is continuously rolled until the total sum of all rolls exceed 300. Approximate the probability that at least 80 rolls are necessary. So the probability x equals 1 equals the probability x equals 2, and so on. And each have a probability of 1 over 6 because they each have the same equal amount of chances to be rolled on a dice. The expected value is computed as the sum of products of x values with the corresponding possibility. So we get 1, 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that equals 3.5. The variance of any random variable is expected value of x squared minus the expected value of x squared. So I put that into the formula, and it's 1 over 6 times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, and you get 91 over 6 minus 3.5 squared, and you get the variance of 2.9167, and the mean is 3.5. And I use 79 rolls because if it's less than 300, then you would know that you would need more than that, and you would have the at least 80. So the summation of xi is an element of n. Mean equals 3.5 times 79. Variance squared is 2.9167 times 79. And you get the mean of 276.5 and the variance of 230.4167. So the possibility of the summation of x being less than 300. So we convert that into standard normal variable, and we get the probability of z is less than 300 minus 276.5, which was the mean, over the square root of 230.4167, which was the variance. And I put this into the z-score calculator, and I got 0.9394. That's the answer.
Okay. All right. Very nice. Very nice. Okay, I just want to present as well. Okay, Ice, you're up. I think everybody did.
Okay. So I did question 8.18. Sorry. And 8.18 just asks to repeat part A of problem 8.2 when it is known that the variance of a student's test score is equal to 25. And in part A of problem 8.2, the question used Markov, which just says that the probability of x being greater than or equal to a would be less than or equal to the expectation value over a. And for that, it just comes out to 15 over 17. And then in 8.18, the question that I did, it asks us to use Chebyshev, which is basically the same thing as Marco, except it utilizes variance when it's given. And it's the probability of x being greater than or equal to the mean plus a is less than or equal to the variance over variance plus a squared. And from there, you could just plug in the given values and solve, and it comes out to 1/5.
Okay. All right. Yeah, that's it. Yeah. All right. Thank you. So that's Ice. All right. Okay, anyone else like to present? I think I have no more to talk about. I think we have covered all the syllabus. Hmm. Oh, not here. Yeah, we are done. We're done with the syllabus. But we have 2 more classes. So 2 more classes. Yeah, Catherine, that's it. Because the law of strong. Yeah. So next Tuesday and next Thursday, to have 2 more classes. And again, regarding the final, I don't know yet. Okay, I don't know if we can do online yet. Let's see if the department chair allows us to do that. So let's see the announcements. So the final exam is scheduled for May 23rd, which is a Tuesday. 23rd is a Tuesday, right? 23rd, yes. It's a Tuesday, 6 to 8 p.m. Ingersoll Building 3413. But since it's so late, I'm trying to see if it's possible for us to take online. And then more or less, I think I know all of you. I know, you know, I have in my mind what kind of grade you are getting anyway already. Or anyone has any questions? Or 6.8? Let's see what's 6.8. Okay, let me share with you. 6.8. Yeah, we did talk about exchange variable, did we? 6.8. We didn't talk exchange variable. We did. Yeah, we did talk about. Oh, no, we didn't talk about it? Oh, why I remember we did talk about it. I remember we did talk about this. Yes, we did. I remember this. You probably missed it, Ron. You can watch the recordings. Just no one did homework, I guess. No one picked a presentation from this. Yeah, we have talked about this. The title is just a little bit different. Exchange variables, they just change it to be joint probability distribution of functions of random variables. They didn't use the word exchange variables, all right? But, oh, that's 6.7. Oh, okay, hold on, 6.8. You're talking about 6.8. Maybe you're right. Yeah, we did talk about 6.7, 6.8. Let's see, the random variable to be exchangeable if every permutation of this in of the integers of n and this equals to for all. So what does it mean? That means the n-random variable are exchangeable if the joint distribution is the same, no matter in which order the variables are observed. So for discrete random variable, yeah, we didn't talk about this. Okay, let's talk about this. Okay, so in this case, exchange random variables just means 6.7 is important for us. 6.8, let's see, we just need to know. Okay. So this is an important concept, which means the order of observation doesn't matter. All right. So we can switch the order of, you see, this is xi1, this is x1, xi2, x2, so on and so forth. So this exchangeable. And if it's for discrete random variables, so if it will be exchangeable if this happens, if all the xi's, right, can be substituted by xi, x1, x2, x up to xn for all permutations of all those I1 up to In. And with the values of x1 up to xn. So this is equivalent to stating that probability of this n of random variables equals the probability of the first random variable represents this, so on and so forth. It's a symmetrical function of the vector. Okay, which means that its value does not change when the values of the vector are permuted. Basically, we just have to think the order of observation of the variables doesn't make any changes. Let's see this example. Suppose that the balls are withdrawn one at a time and without replacement from an urn that initially contains n balls, of which k are considered special, in such a manner that each withdrawn is equally likely to be any of the balls that remains in the urn at the time. So xi to be 1 if the i's ball withdrawn is special. Xi is 0 otherwise. So we will show that the random variable x1 up to xn are exchangeable. So to do so, we let this vector to represent the vector consisting of k ones and n minus k zeros. All right. So k ones, n minus k zeros. However, before considering the joint mass function evaluated at this vector, let us try to have some insight by considering a fixed such vector. For instance, consider the vector 2, 1, 1, 0, 1, 0, 0. The last one is 1, which is assumed to have k ones and n minus k zeros. Then probability of k ones and n minus k zeros is k divided by n, k minus 1 divided by n. So what is this? K minus 1, k minus 2, n minus k, k minus 2, n minus k minus 1. Up to 1 over 1, right? And the denominator is just n minus 1. So we see the denominator is n factorial. The numerator is k minus 1, right? This is for the ones, right? For the ones. Then n minus k, n minus k minus 1. This is for the zeros. So we see we have k factorial, right? And n minus k factorial. So which follows because the probability that the first ball is special is k over n. The conditional probability that the next one is special is k minus 1 over n minus 1 without replacement. The conditional probability that the next one is not special is n minus k because we have n minus k of them over n minus 2, right? Because only left with n minus 2 now, and so on. By the same argument, it follows that the probability of this vector can be expressed as a product of n fractions. The successive denominator terms of this fraction will go from n down to 1. The numerator term at the location with the vector of x1 up to xn is 1. For the s time is k minus I minus 1. And where it is 0 for the s time, it is n minus k minus I minus 1. Hence, since the vector consists of k1s and n minus k zeros, so we have this k factorial and minus k factorial divided by n factorial. Right? So what is this? This is we know this very well, right? Since this is a symmetric function of the vector, it follows that random variables are exchangeable. So this is a little proof. Oh, sorry. No, this is just because, right? You don't have the you don't really have the okay. What you record it? Okay, well, you're right. 6.8. I didn't talk about it, so we'll talk about it a little bit. We're catching up at 6.8. So let's see this remark. Another way to obtain the preceding formula for the joint probability mass function is to regard all the n balls as distinguishable from one another. Then, since the outcome of the experiment is not ordering, so now we have ordering because each ball is different. Of these balls, it follows that there are n factorial equally likely outcomes. Finally, because number of outcomes having special and non-special balls in specified places is equal to the number of ways of permuting the special and non-special balls among themselves. So k factorial and minus k factorial will obtain the preceding mass function as well. It's easily seen that if x1 up to xn are exchangeable, then each xi has the same probability distribution. So for example, if x and y exchangeable discrete random variable, then probability of x equals to probability of x and y. Now sum up the y's. It's the same as the probability of y and x. Yeah. Sum up the y's. For example, it follows from example A that the S ball withdrawn will be special with probability k over n, which is intuitively clear since each of the n balls is equally likely to be the S1 selected. You see this, right? What is the difference from this, from the probability with, so this is all joint probability functions, right? What is the difference? So this is, think about a single variable calculus and the multivariable calculus or vector calculus, right? So it's a similar idea. It's a similar idea. The concept is easy. The concept is not difficult to understand, but just go from one dimension to higher dimensions, from one variable to multivariables, from a real value to a vector value. Let's see this example. In example AA, Y1 denotes the selected number of first special balls withdrawn. Y2 denotes the additional number of balls that are then withdrawn until the second special ball appears. Let Yi denote the additional number of balls withdrawn after the I-1 special ball is selected. until the S1 is selected. So example, if n equals 4, k equals 2, x1 equals 1, x2 equals 0, x3 is 0, x4 equals 1, then y1 equals 1, y2 equals 3. Now y1 equals I1, y2 equals I2, yk equals ik. xi1 xi1 plus I2 equals to xi1 plus until ik equals to 1. So this is 0. Okay, then from the joint mass function of xi, we have, right, list all this, and will still be the same. So this is saying the random variables y1 up to yk are exchangeable. So the order doesn't matter. Note that it follows from this result the number of cards one must select from a well-shuffled deck until the ace appears has the same distribution as the number of additional cards one must select after the first ace appears, until the next one does, and so on. Let's see this example. The following is known as Poisson's model. Suppose that n initially contains n red and blue balls. At each stage, a ball is randomly chosen, its color is noted, and it's then replaced with another ball of the same color. So let xi equals 1. If the i's ball selected is red, let it be 0 if the i's ball is blue. To obtain a feeling for the joint probabilities of this xi, know the following special cases. So the first one is first one is red, red, blue, red, blue. So the probability for the first one is this n over n plus m, because we have n red and blue. The second one is n plus 1 over n plus m plus 1. The third one is blue, so it's m over n plus m plus 2. Fourth one is red, so we have this, so on and so forth. And that is this. And if this one, let's see, so this is how many? We have 1, 2, 3, so 3 red balls, 2 blue balls in different stage, right? Now we still have 3 red balls, 2 blue ones in different stages. So if we do the calculation, right? So blue, so we have m over n plus m. Red, we have n over n plus m plus 1, so on and so forth. If we put them together, we see this is exactly same as the above, right? Exactly same. Exactly same. So that's why the order of permutations doesn't change the probability. But the same reasoning for any sequence of xi up to xk that contains r1s and k minus r zeros. So we have this. We calculated the ones, so calculated the zeros. So for any value k, the random variables x1 up to xk are exchangeable. Right? So that's why from the very beginning saying, the order of observation doesn't change. Let's see this. The interesting corollary of the exchangeability in this model is that the probability that the ice ball selected is red is the same as the probability that the first ball selected is red, namely n over n plus m. For the intuitive argument for this initially non-intuitive result, imagine that all the n plus m balls initially in the n are of different types. So one is red ball of type 1, one is a red ball of type 2. So now we put different, we distinguish each red ball, even they're all red, but they're different. So on. Also, 1 is a blue ball of type 1, and so on, down to a blue ball of M. So for the red ball down to the N, so blue ball, we have M of them. Suppose that when the ball is selected, it is replaced among with another of its type. Then, by symmetry, the S ball selected is equally likely to be of any of the N plus M distinct types. Because N of those N plus M types are red, so the probability is N over N plus M. All right, it's just another way of saying it. Let's see this example. So this final example deals with continuous random variables that are exchangeable. So we have N random variables, independent uniform random variable, and denote that order statistic by x1 up to xn. That is this. So let y1 defines x1 yi equals xi minus xi minus 1. So we want to show y1 up to yn are exchangeable. So let's see. The transformations of y1 equals x1, yi equals the xi minus xi minus 1. I up goes from 2 up to n. So xi equals the y1 plus xi equals y1 plus up to yi. Let's see. That's from this, right? Because y1 equals x1. So y2 would be x2 minus x1. y3 will be x3 minus x2. Right? If we want to find x2, let's see in this case, we have y2 equals to x2 minus x1. So that means x2 equals to x1 plus y1. So that's how we come up with this. So it's easy to see that the Jacobi of this preceding transformation is equal to 1, right? Because all the coefficient is 1. Then from 7.3 equation, we obtain Fy1 up to Yn takes this vector is the same as f of y1 plus y2, so on and so forth down to y1 plus up to yn. So f is joint distribute the density function of the order statistics. Then from 6.1 equation, we have Fy1 equals the n factorial. We have this condition. Or equals the n factorial for yi is in between 0 and 1. Because the preceding joint density is a symmetric function of y1 up to yn, we see that the random variable y1 up to yn are exchangeable. For this kind of proofs, we don't have to worry, all right? Because for us, we just want to apply the theorems yeah. So this is like introduction level. But it's good to know, okay, so this section is just good to know from one dimension to higher dimensions. And with a certain, because they're independent variable, they're independent random variables. So they are exchangeable, all right? All right, so this one, that's it. It's just to know this one. And Paul, thank to you. Right, I didn't talk about this. It's just good to know. All right, we don't really have to do. I'm not going to give exams on this, so not to worry about that, because a lot of them involve proofs. Oh, chapter 8 is only one section. You only have to choose from one section. Chapter 8. Yeah, chapter 8, I guess we only learned Chebyshev and Markov's inequalities. And the law of large numbers is hiding in the central limit theorem. And if you could choose, let's say 8.3. Does 8.3 have any homework? Yeah, anything use calculators. We don't need to. All those use calculators. Yeah, you may choose some homework for 8.3, right? Yeah, choose some from 8.2, 8.3. All right. Okay, okay, Catherine, you want to present another problem? Sure, go ahead. I know you want to earn your presentation credits. Yeah, sure, some interesting questions. Yeah, go ahead.
I don't know if it's right, but I'm gonna try it.
Oh, sure. Catherine, are you talking? Can I hear you?
Sorry, I was talking. I was muted. I'll start over.
Okay, let's start from the beginning.
So each player of a soccer team has to shoot a ball at a distant target until 3 successive hits are registered. Let P denote the probability of a player hitting the target. Obtain an upper bound for the probability of a player needing more than 10 attempts to successfully hit the target. Let P be estimated at 0.8 for successful players. These players claim that they will not exceed 10 attempts more than 10% of the time. Is their claim in line with the bound obtained? So the probability of x equals the combination of x and p to the x parentheses 1 minus p to the n minus x power, and the combination of r and n equals n factorial over r factorial parentheses n minus r parentheses factorial. So in this case, n equals 10 and p is 0.8, and that was already given. So the probability of more than 10 attempts equals the probability less than 3 success in 10 attempts. So that equals probability of 0 plus probability of 1 plus probability of 2. And I just plugged the numbers in, and I put them in their matching orders to what it belonged to. When you add them all up, I got 0.0000779,264, and that's less than 10%. So I would say the claim is correct.
Okay, so there's a binomial distribution. All right. Okay. All right. Thank you, Catherine.
Professor, I have a question.
Yes.
Chapter 8 has been done. We don't have to move on. But,
Yeah, we don't have more.
okay. Thank you.
Unless you suggest something. I don't think we have anything more to talk about. Let's go to Yeah, strong law of strong law of large numbers. I think it's good enough for us to know the weak one. How many questions will we need to do for chapter A? I think 10 questions, right? 8.2, 8.3. 8.2, 8.3. Yeah, that's it. No more new material for us. So next 2 more classes are only for presentation. All right. Yeah, I know you guys work so hard. It's yeah, you deserve some rest. For those of you needs to catch up, you still have 2 more. We still have 2 more classes for you to catch up. Okay. And anyone has any questions? Just write down our final date and time. All right. If you have no questions, you are a free bird for tonight.